in the back? Is that okay? Good, thank you. Just first, a few things. I apologize for the first part of my slides not being in the handouts. They will be on the web page, so Vichy tells me at some stage. And you could also find more on our work, where we discuss some of the applications we've been looking at. And so I'm doing a little bit of advertising. I hope that's okay with you guys. On our web page, and the web page is sort of easy. It's data mining. .anu.edu.au. And at some stage I might have my slides on there too. I have slides from other talks on that web page. Now just what we want to do today, what I would like to do today is continue on what we did yesterday. At first I'll try to maybe clarify a few things which might have been not so clear. I hope that after Vichy's very nice exposition before, a few things got a little bit clearer and you got to see a few things I talked about from a slightly different but related viewpoint. There's one thing, there were a couple of questions yesterday. There was one about, the generation of this reproducing kernel Hilbert space by completion. I think Adam is not here now, huh? So I'll tell him some other time. I mean, one argument you could use there is a mathematical theorem called the Hahn-Banach theorem, which relates to extending linear functionals from subspaces onto your full Hilbert space. That was one comment. About our maybe relating what we're going to talk about to what we heard before. Remember we had this, sort of still trying to use these pens here. They're too big and too thick for me. So let's see if this works here, huh? Okay, huh? So we have our phi, the scalar product which Vichy and Alex talked about. And I just want to sort of show a couple of examples. Would like to remind you. So this is a function of x, right? A function of x. And in the case of normal distributions, we have eta 1x plus eta 2x squared. So our phi of x is, and Alex sort of discussed this in some detail, consists of the vectors which has components x and x squared. And our eta has these two components, two parameters, eta 1 and eta 2. Now maybe if you wanted to look at it in a bit more general, you could say, well, maybe in some cases this function might be a periodic function, or a function on the interval 0, 1, or 0, 2 pi, say. And in that case, you could represent this with a Fourier series. And the Fourier series looks like this here. So we have eta k, e to the I kx, and k sum from minus infinity to plus infinity, right? And so now if you assume that you look at the space where the sum of squares of the absolute values of your eta k is bounded, you get exactly the L2 functions on the interval 0, 2 pi. So the square integrable functions. So this is already a Hilbert space. Now, how do you get the reproducing kernel Hilbert space here, in this case? Because we know, that our L2 is not a reproducing kernel Hilbert space. Well, the trick here is to put penalties onto these eta k's, right? So instead of looking at, scalar products in that space, which are just the sum of the squares of the eta k, we actually say we look at the case where our sum of eta k squared times k squared, say, k goes from minus infinity to plus infinity, where that is bounded. This space here is exactly the same as our Sobolev space H1, which I mentioned yesterday. And because if you look at the first derivative here of this function, you see that you get a multiplication by k, and then if you take the norm of that, you get exactly this here. Well, maybe you'll have to add 1 here if you want, I mean, maybe we should really take k squared plus 1 instead of k squared. But that's sort of the I mean, that doesn't make any big difference. That's sort of the key observation. This is how we get our Sobolev space and our reproducing kernel Hilbert spaces into here. Then you could ask yourself, what is the reproducing kernel here in this case? What is the reproducing kernel as a function for this norm where we use this Sobolev space? It's a question I'll leave to you to figure out. It's not too hard. Then another example. So what we will be using, we want to approximate more general functions here. So we want to approximate general functions. How do we approximate functions? Well, we have a function space, a finite dimensional function space, and in that function space we have a basis, a finite number of basis elements. For example, we want to approximate by polynomials, right? There we can take as basis functions maybe the monomials, 1x, x squared, x to the third, and so on. Or maybe slightly better, Chebyshev polynomials as basis, right? Or we could use splines. Has anyone heard of splines? One-dimensional polynomial splines before here? Yes, so I see a few people. So we could use, piecewise polynomial functions or splines here. And there we could use the so-called B-splines as a basis. That's a very sort of computationally very nice basis. And so here, what I'll write is that the business we're in is that we're looking at approximations of the form I equals 1 to m of eta k bk of x, right? And then we assume that we have given these b's, right? And we want to figure out what our coefficients are. I think the underlying theme here is sort of try to get some sort of linearity back again. I think that's what the kernels really do. They bring you back from a nonlinear problem where you have to find a boundary between two classes which is sort of wildly curved, and you want to use methods from linear models. The support vector machines, for example. Right. So that's the key idea. You want to use these techniques using linear models. But that's exactly what we're doing here too. Because while this here it's not linear in x, so you have to forget about that. That's too strong an assumption, but it's linear in our coefficients eta k. So that's the key thing here. And here again, here we have the linearity in these etas. I think that's some of the key points to remember. So we're in the same business. But what comes as an additional parameter here, and that's what I'm talking about, that makes my talk may be different from some of the other talks, is that we're looking at approximating these more general function classes in our finite dimensional function class. Now, what do we want to do with these things? Well, basically, we've been talking about optimization problems. Vish has been talking about optimization problems. Alex has been talking about optimization problems. So we want to find some minimum of some function, maybe, or some maximum. So in general, and the function that depends on eta, or more generally, and I'll call this here, I think Vishy called this here t of x, is that right? I think if that's okay, I'll call it f of x here. So what we want to solve is a minimization problem for eta, or equivalently an optimization problem for our f. So we want to find, for some functional j of f, we want to find the function which minimizes this. And so I think Vishy gave a couple of examples for this here. Just the maximum a posteriori case. We have things like which look like this here. We have the sum of I equals 1. And I'll just look at this very simple case as an example, minus yi, where these are our data points. So we have the residual squared plus some term times some norm of f. I'll put this here, 1 here. This is the norm in our reproducing kernel Hilbert space, which corresponds to the norm of the coefficients eta. Okay, so then we might have, an additional term, our log partition function, but I won't talk about that at this stage. I'll look at this simple problem. So the point here is, just another, comment, computational comment maybe, about the choice of this norm here. The question was raised in the last hour, how do you choose your kernel? Right, how do you choose a kernel? That's an art, as was said, I think. And, it's maybe not easy, but it's, you can gain some insight if you understand your underlying design, right? And Alex, I'm sure, has a few comments here.
Well, for instance, in the case of density estimation, this really corresponds to, well, should you model your data by a normal distribution or a Laplace distribution or a Poisson distribution? So, that's the very same question.
Right, yes. Exactly.
That's the statistician's job.
Yes. Okay. So I think he took a great way out. So we loaded all onto our statisticians, right? And there might be some other statisticians here, I don't know. But the thing is, I think what Alex also said is, the choice of this norm here of our reproducing kernel Hilbert space, of course, is the same as the choice of our kernel, right? So these two things are equivalent. Once you know the norm, right, implicitly you can get your kernels through solving, the elliptic problem which I showed you yesterday. So choosing the norm or choosing the kernel, that's the same thing. So I would say, let's assume we have a norm, right, and then you also have a kernel. Right? Of course, on the other hand, you can go the other way around. Let's choose a kernel, and then you also get a norm. It's interesting. If you look at the radial basis function literature, there have been these two approaches. And you look at recent work by Schabak, for example, from Göttingen in Germany. There they start like the statisticians did. They start with your radial basis functions, or your kernels, and then from that they define a norm. If you look at the thin plate splines, there they start with the norm, and I'm sorry, I should have a square here. You start with the norm, and then implicitly you get your radial basis functions. Okay, but let's assume that we know that. So what we want to do, we want to minimize this here. And what we do, we take, one of these things here and put it in here. So in fact, what I'm interested in is taking this here and putting it into here, and we'll compute these eta k's. So now, okay, so with Alex's way out, we have our kernels. The statisticians told us about the kernels, so that's fine. But there's still another problem. What is the other problem we need to solve? If we want to minimize, we want to minimize this here. We want to minimize this here to compute these eta k's. But for that we still need something else too. We need to choose something else, right? And that is, we need to choose these basis functions bk. Right? In particular, we need to choose the space, the approximating space, but also the basis functions. And that's what I'm going to talk about. So I hope did that make the sort of context a bit clearer? Okay. So the last time, and typically, if we have an interval, so here the interval from 0 to 1, what I'll do, I'll look at functions. So we'll look at the whole class of approximations, a sequence of approximations. So the simplest one would be a constant function, where we have a basis function which looks like this here. And then we'll look at the next one, so we have one grid point for that. Then we have linear functions, where we have an additional basis function, which maybe corresponds to the grid point here. Then we have, this is 1. Then we have a third basis function, which looks like that, right? And then we have a fourth basis function, and so on. So then we have these. So we could use these as basis functions, right? For example, this so-called hierarchical basis, and I'll talk a little bit more about those. But what sort of functions we get is we get functions which are linear between our grid points and which are continuous. So piecewise linear functions. And our grids I'll always assume that we have grids of the size 2 to the n plus 1. So, we have, except for n equals minus 1 if you want, right? First we have one grid point, but then if we have n equals 0, we have 2 grid points, then we have 3 grid points, and so on. So this is the n in our grids. And all our approximations we'll look at are based on this simple piecewise linear scheme. So then you could say, okay, if you go to higher dimensions, because that's what we want to do, we want to have x, our x here, is an element from Rd. Now, we don't have to take Rd. We could take, some other set. But we'll assume here, for this discussion, that this set is a tensor product of simpler sets. So our feature, or our x, our feature vector x, has a number of d components, right? And the first component can be continuous, right? The second one can have a certain finite number of values, can be categorical, right? And so on, right? It can have all sorts of components. Some of the techniques, the sparse grid techniques, they are also applicable to these more general situations as well. But at this stage, I'll talk about this case where we have d real features. So now you could say, okay, if we have a basis in one dimension, right, which are our hat functions, right? These are the simplest type of B-splines you can imagine, in a way. Or maybe the second simplest, if you want. In high dimensions, what you do, you just take products of these one-dimensional functions, right? So if you have 2 to the n plus 1 basis functions in x1, then you have 2 to the n plus 1 squared basis functions in x2, where the basis functions are just, bi1 of x1 times bi2 of x2, right? Or in d dimensions, you have this situation here, where you have the power d if your grids are in all dimensions are of the same size, right? Which doesn't have to be, but let's assume this now. Okay, so yeah, I'm sorry the n here and the n up there are slightly different things. Let's call this here m. So what we do, we assume we have such a basis, right? And then we want to solve our problem, our optimization problem here. But you say, well, actually, we could use our kernels from before. That's true. But we observed yesterday that we get large dense linear systems of the size of the number of our data points n. And so we get, iterative solutions would take order n squared at least, because you have to do at least one iteration, and you have n squared matrix elements. A direct solution would be of this order. And of course, we might want to solve many problems. So actually what we want to do is we want to look at our final dimensional space. So that's defined by our basis functions. And here we sort of control this space, or the linear systems we get are sort of controlled by the dimension of that space. But now if we look at the RD, we see that the dimension of our space is very high. It's exponential in the dimension of our underlying domain. Right? So that means if we take twice as many grid points in each direction, we get 2 to the d times as many grid points overall, or coefficients, because the number of grid points here in this case is the same as the number of coefficients. Now this is a problem if d is 100. I forgot now exactly what 2 to the 100 was, but it's roughly 10 to the 30. So this is a big number. We wouldn't be able to typically solve a problem of this size. So here comes sparse grids come in. So what we want to do, we want to find a space which somehow has basis functions which are a little bit like this here, but has a reduced size. We want to reduce the problem size. So how could we do that? We could do some sort of compression. We could say, okay, let's look at our basis vectors and just throw the ones away which are small. But I mean, this can be a bit of a problem. The key thing here is to choose good basis functions that are one-dimensional functions. And for example, we can choose Fourier or maybe eigenvectors which can relate to our kernels. And look at products of those, but only sort of a certain number of products of those. And I'll try to give you a feel for that. You can also base it on wavelets or on hierarchical basis functions, which date back again. This is, again, early mathematics in the 1900s by Faber, picked up by the German mathematician Henri Iseventien in his thesis in the 1980s. The hierarchical basis functions are exactly the basis functions which I have here on the board. And I have them displayed here once again. So as I said before, the first basis function, this is from 0 to 1, is just a constant function. Here we have a linear function. Here we have the coarse hat. Here we have a slightly sort of finer hat, which has a support on the lower half of our interval. And then we have another hat. So these sort of belong together in the sense that they have the same scale. So you see here our basis functions, they encode a certain scale, which is given by the width of these basis functions. And here you have 1, 2, 3, 4 basis functions which have a finer scale, and then we have even finer scale. So if you sort of count these together and say, linear combination of these two is one subspace which we'll call T1 maybe. S0 we'll just take these here together. So S0 is just the space of linear functions. S2 is the ones over there. S3 are the ones which are generated by these 4 functions here. Note also, an interesting side effect here is if you look at just one scale in this T3, these basis functions are of course all orthogonal with respect to the L2 norm because their supports are non-overlapping. So if you multiply them with each other, you get 0. That's why the scalar product is 0 too. So we decompose our function, in this case, as a sum of a linear function plus these components which correspond to certain scales. And now the intuition here is that your components with smaller scales are smaller. So the smaller you take the scale, the smaller that component it is. And does anyone have an idea what that relates to? What sort of properties of the function that relates to? So why would these things get smaller? Or you might, those who are familiar with signal processing, if you look at your Fourier coefficients, the Fourier coefficients for higher frequencies, they drop, they get smaller. And the speed with which these things drop tells you something about the function. What does it tell you? Smoothness. Yes, exactly. Thank you. Yeah. So that's exactly. So if a function is smooth, these things drop, these components, they drop very quickly. And that's what you have here too. So the size of these components drops very quickly for smooth functions. Okay, so then you can do this in 2 dimensions, and here I just wanted to indicate what your grid points is. So this is a typical picture. So here we have constant functions with a grid point here in the corner. Here we have one grid point here, which means that our functions are linear in this dimension and constant in this dimension. And here we have a grid point here, which means that they're this hat function shape in this dimension and constant in this dimension. So it's like a roof, I guess, right? This function here looks like a roof. And here we have, one basis function here, the other one here. And then we have combinations of these 2 things. So here we have a so-called bilinear function, which is just a function x1 times x2, and so on. So here you get a sort of a hierarchical basis. And what I've drawn here is actually these things on diagonals, and drawn them with the same color, because you can show that the components corresponding to all the functions on these diagonals are roughly of the same size in many cases. And that's the basic observation for the sparse grids. And what sparse grids does, instead of approximating your function with the full sort of gamut of your basis functions, which takes everything down here as well, it cuts off at a diagonal. And you can see that that gives you a substantial reduction in your complexity. We'll talk a little bit more about that. Now, mathematicians, they often look at boundary value problems. We want to solve Dirichlet's problems, differential equations, and often we have 0 boundary values. So here we have some basis functions with 0 boundary values, and the grid points are here. So this is where our function is 1, right? And all the other grid points, our functions are 0. Yes, Marcus.
Are these grids the grids by Zenger, or are these more?
Yes. No. These grids are the grids by Zenger.
But it seems that you only save a constant factor. So in d dimension, you just save d factorial or something. In 2 dimension, you just save, instead of taking a full grid,
yes,
which is a square, you
yes,
just save a factor of 2.
Yes. Good question. Yeah. Okay. Did everyone hear the question? So the question is that if we just cut off the lower half, we only cut off half of everything, basically, right? So if I put it this way, Marcus sees straight away that that's not the case. Because what happens is that you have to look at the density of your grid points to see how many coefficients you have. So here on this line you only have 1. Here you have 2. On this line you have 4. So which means that you have 4 degrees of freedom, for this block here, right? On the next line you would have 8 degrees of freedom here and here. And down here you would have 16. Right? So out here you would save straight away 32 degrees of freedom just by leaving these 3 things out. So if you do this more systematically, the complexity of your sparse grid reduces from n to the d almost down to n. Not quite, not quite. So I see Jochen is very suspicious about this because, I mean, what you get is something like n times log n to the d, right? So, or d minus 1. So you still have some exponential dependency in there, which is a bit of a problem. But these are these classical spaces, and these are the dimensions which I just talked about now. The size of the components. This is what I mentioned. The size of the components relate to the approximation in your piecewise linear spaces. And this relates to the error formulas we had last time. So that's why you get basically here this 2 to the minus 2n. This is like an h squared. Right? So these components really are of that size of the error. And in 2 dimensions you get this here, d dimensions. And so here's the definition of our classical sparse grids, where our T alphas are really the tensor product of those one-dimensional different spaces which only had corresponded to the smaller scales. So in a sense, what this is, this norm of alpha is just the sum of the sort of the indices of your components. Is something like an overall scale. So if we go back again, just to illustrate that in this picture here, here we have, this. Here we have scale overall scale 0. Here we have 2 and 3 and so on, basically, right? So basically we sum over the diagonals. That's what this formula here means. And we throw everything away. All the other spaces we throw away. So most of the spaces we throw away. And so now if you draw again our diagram which relates to the dimension of our space and the potential reduction in error, we get, instead of this diagram, we get this here. So now if we look at the 1, 2, 3, a 6-dimensional space, we see that if we want a sort of a reduction of 10 to the minus 5 or something, say, in error, we have to have a space which is 10 to the 8 times larger. So that's starting to almost get reasonable. If we wanted to do the same here, we needed to go over 10 to the, we needed to go to 10 to the 17, which is clearly not feasible. So this is the curse of dimensionality. By the way, I mean, many of you might know I think the term curse of dimensionality was first introduced by Bellman in the 60s, right? In his book on, what was it called? Control and, what was it called again, Alex? Something on control.
Give me a minute.
A guided tour to control, adaptive control, something like that. Yeah. So classic.
Control process is 1961, Princeton University.
Okay, thank you. Yeah. So and of course Bellman, he thought about 5-dimensional spaces, maybe 4-dimensional, maybe even 3-dimensional spaces, right? And there you had the curse of dimensionality already. But now we can sort of maybe handle 3-dimensional spaces. But certainly if we want to look at 100-dimensional spaces, functions of hundreds of variables, we cannot. So now I'd like to introduce a more general concept. So those of you who had difficulties, with the approximation and these piecewise linear and multilinear spaces, here we go back to a sort of a more general definition of our sparse grids. And we start with a regular grid. So a regular grid looks like this here. And we always assume that our grid lines are of the the grid sizes are of the size 2 to the minus L or something, right? So they're basically a binary, if you want. And then we define a generalized sparse grid. So that this is a grid here, just as a union of ordinary grids. So we just take the union. So we take, we have this grid here, and we take another grid, which has maybe a different collection of grid lines, and then we take the union of those, and the corresponding space of piecewise bilinear function is just the sum of these spaces. So what does this look like? Sorry, where did I go now? I went the wrong direction, huh? So here are our regular grids. So here is the whole sort of lattice. You can see that the grids, these regular grids we look at, they form a lattice. So if we go down here, this grid is a subset of this, and this here is a subset of this, and a subset of this, and so on, right? So you see we have a lattice, and every sort of intersection of two of those grids is again a regular grid, right? So that's you have the usual lattice properties. Of course, the union. So watch out with lattices. You would think, well, of course, in lattices the union would have to be a lattice, a point here as well. Well, in fact, that's not what we're going to use as the supremum in our lattice. We're not going to use the union. But we're going to take that grid, which is the largest grid which contains both. So instead of the union, if we take these two grids here, the grid which is the lowest upper bound, right, because that has to exist in a lattice, is this grid here. Right? So it's not the union. It's not like the lattice of sets. Okay, so here we get, and so here are a couple of examples of what type of generalized sparse grids we get. So this is a regular grid, right? So we have a function which is constant in this direction and linear in this direction. Here we have a function which is linear in this direction and constant in this direction. If we take a union of these two things, we get this here. What sort of function does this correspond to? A linear function, right? That's right. So this here is a linear function. So in fact, in our sparse grids, we can actually represent our linear functions. So we don't need, in regular grids, we would have this point here too, which would give us the bilinear functions. And there we would need constraints to take out the linear function. So that's a nice property of these generalized sparse grids, that we get the linear functions as well. Here's another example. Let's take these three grids. Let's take their unions, right? The union, again, as I said, is not a regular grid, but is of, looks like this here. What one knows is that in many cases, especially the case of the classical sparse grids, the approximation properties of your union of your grids is very similar for many functions, for smooth enough functions, to the approximation of the grid which you would get if you would take the least upper bound of these functions. So this is, thanks Jochen, this is from Jochen's thesis. I hope that's okay.
I also borrowed from somebody else.
Okay. From where?
Somebody from the second school.
Okay. Okay, so Okay, so this comes sort of from almost from the source, I guess, right? And this is what a three-dimensional classical Zenger-type sparse grid would look like. So you can see you have a little bit points everywhere in a sense. Here are, again, classical grids. So here you can see properties, typical properties, what you have. So in this case, this is the case where we have boundary value 0. Here's the more general case. What you can see is that the boundaries, the outside is covered better, and the further you get inside, in a way, the less coverage you have. Right, so that's a property of these grids. Now, of course, we need algorithms. And, yes, please.
Why would you waste more? It's almost like you're putting more weight on the boundaries.
Yes.
More interesting stuff is going on in the middle.
Right. Okay. Okay. So the question is, why would you put more weight on these boundaries, especially, I guess, in this example here, where maybe what the more interesting things are going on is right here in the middle? Right, a good question. And I think the answer is, well, yes, you are putting more weight on the boundaries in a sense. I guess you could maybe go to something more like this here. You could actually have something which is which approximates your interior better in a way. But the thing is, the coverage is not sort of at the boundaries sort of better. It's not an adaptive scheme in a way. So we don't know a priori where the interesting things are going on, right? And the way we approximate is by functions, by sums of functions. And I think I'll talk a little bit more about that later on. It has to do with sort of interaction splines. Has anyone heard of interaction splines at all? So, or has anyone heard of analysis of variance? Yes? 3 people? Good. So in analysis of variance, you have main effects from your variables, and you add those up, right? And then you have effects of interactions between the variables, where you have functions of 2 variables, and so on, right? And that's what's happening here too. So this here basically corresponds to the fine resolution. So you have finer resolution of your main effects. And then the higher and higher your order of your interactions get, the coarser, the coarser the grids, the corresponding grids are. So maybe that's a slightly statistical answer to the question. I think we'll make, like Vichy, a 3-minute break here. If that's okay.